Okay, so let's get started. As you said, my name is Dereka Carroll-Smith. I am a PhD candidate at the University of Illinois in the Department of Atmospheric Science, and my PI for Blue Waters is Trapp. So today I'm going to be discussing some of the bases of my dissertation research titled Hurricane Spawn Tornadoes Under Anthropogenic Climate Change. So I'll cover what's the problem, why it matters, why I need blue waters to solve my problem. So I'll go over the methodology and some preliminary results that I have. So what's the problem? Given TC climate projections for the future, we want to know how will anthropogenic climate change impact TCT generation in a mid and late century climate. So getting to tropical cyclones and climate change projections, globally there will be a likely decrease or no change in global frequency of TCs, but those that form are expected to be more intense. There's low confidence for region-specific projections such as the North Atlantic, and the changes in TC activity are highly correlated with the spatial changes in sea surface temperatures. So regionally for the North Atlantic, in the first column you have the total annual frequency of storms, and so you see a decrease in storms, but there is high uncertainty in the decrease. However, for the second column, you have the annual frequency of Category 4 or 5 storms, and although there is an expected increase, there's still much uncertainty with that. There is more certainty with the lifetime maximum intensity in the third column, as well as the precipitation rate within 200 kilometers of the tropical cyclone center. So now looking at the distribution of tropical cyclone tornadoes, you see there are a large number of strong tropical cyclone tornado events occurring within 500 kilometers of the coast. So those blue dots represent F2 and F3 tornadoes that occurred between 1995 and 2010. And so 50% of the most notable TCT outbreaks actually occurred within the 2004-2005 seasons, with Hurricane Ivan holding a record at 118 tornadoes. 80% of TCT outbreaks occur with landfalling storms at a Category 2 or higher. So TCT outbreaks most often occur with the more intense storms, and 83 of the U.S. landfalling TCs between 1954 and 2004, 22% were considered outbreak TCs. And of those 18 outbreak TCs, 78% were Category 2 or higher. So why does this even matter? A report 17 years ago showed that 63% of TC-related fatalities occurred inland. And so when we look at tropical cyclone fatalities, a more recent assessment showed that rain and tornado-related fatalities due to tropical cyclones were actually a lot more likely to occur than storm surge. So the purpose of this presentation, this research, is to investigate the impacts of anthropogenic climate change on the generation of tropical cyclone tornadoes, and to understand the changes in the tropical cyclone tornado kinematic and thermodynamic environments so that we can draw awareness to these inland TC threats. So this really matters in terms of evacuation. So you're evacuating people from the coast, but they may be placing themselves in the path of tropical cyclone tornadoes or flooding. And so overall, we hope to improve the resilience to tropical cyclone tornadoes and reduce those fatalities that we're seeing occurring more inland, and this is our broader impact. So why do I need blue waters to solve this problem? Ultimately, this is a multi-scale problem that really requires a relatively long time integration over a large domain. So the outer domain is covering the United States. And this additionally requires high-resolution subdomains that we really don't know beforehand. So this spatial and temporal, I keep getting twisted. This spatial and temporal domain are required for multiple realization so that we can characterize or quantify some level of uncertainty. So here's the WRF setup on blue waters, a few key features. So our outer domain is 9 kilometers. The interness is 3 kilometers with a smaller domain at 1 kilometer. And the resolution that we chose for the inner two nests are sufficient to resolve not only the TC rain bands, but it's also considered convective permitting. So the case study that I'll be discussing today is Hurricane Ivan. Ivan made landfall on September 16, 2004 in Orange Beach, Alabama as a Category 3 hurricane. It caused over $26 billion in 2016 USD damages, a total of 92 deaths, with 25 deaths in the US, and of that 25, 7 were due to tropical cyclone tornadoes. Ivan wasn't just notable for its 118 TCTs, but also for the significant amount of flooding that it produced in the eastern portion of the United States. So here is a plot of Ivan's tornado reports. And so our inner third nest will be covering Florida, and I'll be discussing that soon. So now I'm going to talk about some results. Our first and second domain was initialized 2 days prior to landfall. The third domain was initialized right when we knew a TCT report was made around September 15th at 18Z. So some results we have comparing our control case with our observed track. So what you'll immediately notice is that looking at the blue for the control and the black line represents the IB track for Ivan, is that our control case doesn't do really well initially over water. However, post landfall, that error is reduced as the intensity converges. So looking at our control versus our observed track, the control does fairly well up until you get into Virginia, and that's during Ivan's extratropical transition, and WRF has a weird way of handling that right now. So here I'm showing a plot of reflectivity, and so here we can kind of glean the structure of our control and compare that with observations. And to me, my control simulation does pretty well with what we see structurally with observed Ivan. And so now going into the 1 kilometer nest, we get to see a more detailed structure of the TC rain bands, and what you'll notice are these, okay, that doesn't work. So you'll start to see these supercells that are forming in Florida. So a way that we can characterize the TCTs, since we are not explicitly resolving the tornadoes themselves, but more so their mesocyclones in our 1 kilometer nest, we're going to use updraft helicity, which is basically a measure of rotating updraft. And we're going to create some threshold and call it potential tornadic mesocyclones, or PTMs. So we need a way to quantify our potential tornadoes to observations. And so updraft helicity is basically the integral of the product of vertical velocity, W, and vertical vorticity, zeta, between the 2 kilometer and 5 kilometer layers. And so this threshold will be used to filter out our PTMs, and I'll be using the 99.9% UH max value over that time integration, specifically because tornadoes are an extreme event. So you want to filter out all of those lesser values and get the more extreme values of UH max and say, okay, this could potentially produce a tornado. So seeing how that works for us, so what you get with our PTMs is something sort of a track. So you're not getting exactly, okay, this storm right here produced a tornado, but more so the tracks of the storms that potentially produced the tornadoes, and comparing that to observations, it does pretty well. So what we have to keep in mind when comparing storm reports is that you're comparing a known event to something that could potentially happen, but you have to keep in mind, just because you didn't see it, it doesn't mean it didn't happen. So just because a storm isn't reported, such as in southern Florida, that doesn't mean that it didn't happen right there. It could potentially mean that there was no one there to see it and report it. So another way that we can mitigate this issue is by using rotation tracks. And so rotation tracks will give us a better account of what actually happened that day, and we can use those tracks to compare to our PTMs. So just a summary of our control versus observations. The control simulation is weaker than Ivan over water, but the simulation data to track agrees well with observations. The observed IVAN and control shows similarities in IVAN's general structure. The inner 1 kilometer nest resolves the cells that appear capable of producing an actual tornado, and our PTM hits were in good agreement co-located with the TCTs that were actually reported. So given this control now, we can look at how this will change in the future. So the approach we're using is the pseudo-global warming approach. And so what this means is that we'll conduct a controlled simulation of a historical event and then re-simulate it with 3D meteorological forcings that has been modified by climate change deltas. So essentially, given temperature, our new temperature for our initial and boundary conditions will be equal to the current temperature plus some climate change delta of that temperature, where delta T is equal to the future minus the past. So these are 10-year monthly means that we'll be using for the month of September. MyRock 5 is the climate model that I'm using currently, and I'm looking at the worst case scenario 8.5, which we're on that path anyway. And it's the first of 6 experiments that I'll be conducting. So now looking at the comparison of these two. So our PGW IVAN actually was more intense landfall than our control case, but both were still considered a Category 2 hurricane. But as it made landfall, the intensities basically converged and were in agreement with each other. Looking at our track, the PGW IVAN actually made landfall in Louisiana, and a fun fact about that is that IVAN was actually forecast to make landfall in the New Orleans area, and they had mass evacuations that did not go so well. Thank God it shifted east at the last minute. So now we can look at the 3 kilometer reflectivity. So you don't see too much difference, but what you will notice is that the stratiform rain area is a lot wider and a little bit more intense in our PGW than in our control case. So looking at the 1 kilometer reflectivity, what you'll notice immediately is that with the track shift in PGW, you have those supercells, the supercells that have also shifted more into the panhandle of Florida. So now the more interesting results. So in our control simulation, we had 2,402 points that exceeded that threshold for our control. With our PGW, we had 4,371 PTMs. And what you'll notice is that although they're in the same area, those contours are a lot wider, which could make suggestions that not only are there more that these storms are not only more intense, but they also could be a lot larger than the mesocyclones that we're used to seeing in today's climate for tropical cyclones. Looking at a density distribution of the updraft helicity, what you'll notice is that the PGW curve reduced its peak. And so you have a wider spread of UH max values. However, these values are biased towards the higher end extremes. So just a summary of these findings, we simulated a viable control, and the PGW is more intense than the control prior and up to landfall, and it also made landfall west of the control case. The PGW produced 1,969 more PTMs than in control, which is suggestive of more and possibly larger mesocyclones in a future climate, and there's a larger spread of UH values in the PGW simulation versus the control, and this increase in the range of UH max values under pseudo-global warming, especially towards the higher end extreme values, is really interesting. So future and ongoing work, we're gonna basically repeat this process for 2 additional GCMs, global climate models, and look at the mid-century and compare that with the late century to see, okay, do we need to be worried sooner rather than later? And we want to assess the range of uncertainty amongst these results, as well as look at the changes in the kinematic and thermodynamic environments to understand, are these storms getting larger, and if they are, what exactly is causing it? I also want to apply a 4th nest over a much smaller region so I can document the changes in the TCT supercell structure, looking at the depth and size, because TCT mesocyclones are dwarfed or miniature supercells. And then I want to use a verification method using the rotation tracks versus solely storm reports. And finally, pair that with demographic data, a disaster risk index that I've created for my master's, because ultimately this is why we do it. That's what keeps me up at night. So with that, I had a few challenges. Just because your control case works does not mean the pseudo-global warming case will work. And I found that out the hard way last week and had to redo my control and everything else along with it. My radiation scheme apparently did not agree with my perturbed climate, so that was an issue. And there's a limit in how large I can make my 1 kilometer domain, so that was kind of tricky figuring that out. And finally, I'm still working on getting my 4th domain to work. It doesn't matter how small or large I make it, it just refuses to run. So WRF is very volatile, and yeah, that's fun. So it's not Blue Waters, it's WRF. Finally, I want to acknowledge the Blue Water Supercomputing Facility for allowing this work to even be possible. My advisor, who's the PI and a Blue Waters professor under modeling of storms under climate change, for trusting me to present my research here. And then my dissertation committee, Ryan Shriver is actually here. He presented yesterday. The NSF GRFP for allowing me to study exactly what I wanted, how climate impacts weather and how the weather impacts society. So with that, I'll take questions.